Hi, I'm Jason Mears and I'm going to talk you through the history of the data center, section 2, computer hardware components. So the first thing we need to talk about when we're discussing computer hardware components is the motherboard, the circuit board that everything else plugs into. Sometimes called a main board or a system board, usually green and usually in the bottom or the side of the computer, and this is the place where all other cards and peripherals plug into. Common names you'll see associated with motherboards would be people like Intel and AMD, companies like Gigabyte and Asus amongst others, but these are names you'll commonly see associated with motherboards. The next thing, probably the most important thing in the computer now, is the CPU, or the central processing unit, which most people would refer to as the brains of the computer. This brain of the computer processes data and performs calculations, and this CPU, or central processing unit, sits on the main circuit board or motherboard in what we call a socket. And we can also describe these processes in terms of cores and threads. And you'll also again see some common names, people like Intel and AMD or ARM, or companies you'll commonly associate with things like CPUs or central processing units. So if we start first with the socket, this is the place on the motherboard that the CPU plugs into, and sockets can be populated with a CPU or left unpopulated or empty. So the socket is the place on the board that the CPU sits, and a socket can be populated or unpopulated. So cores are the number of independent brains on each CPU or central processing unit, and things get a little bit complicated here because older CPUs only had a single core, which now has led to confusion between CPU and cores with more modern versions. So you have this situation where in previous iterations one socket meant one CPU, meant one core, whereas now we have multi-core processors. So we'll talk about those cores next. So we've got full cores, and we've also got hyperthreading cores, or SMT cores, simultaneous multi-threading. So hyperthreading, which is the Intel name for this technology, or SMT, simultaneous multi-threading, which is AMD's name for this technology, it allows a single core to do two things at once. But a hyperthreaded core, or an SMT core, isn't exactly as fast as the original core. In most estimates it gives you between 25 to 40% of the speed of the parent core, but to the operating system it looks like another full core. An easy way to think of this is it's like having an adult that comes to work and brings the child along with them. The adult and the child are two people doing the work, but it's not the same as two adults doing the work. The core, or the hyperthreading core, is always a slightly smaller child one that's not as fast as the original one. And the reason this is important is if you add up the number of full cores or real cores and then any hyperthreaded or SMT cores, when you add the total of these together we get something called software threads. And software threads are what applications and services use to run on a computer. So the more execution threads you have, or the more cores and hyperthreaded cores or SMT cores, the more threads you have, the more things you can run on a computer, or the faster you can run something on a computer. So just to iterate, sockets are the place that a CPU plugs into the motherboard. A full core is a full independent brain, the parent, for want of a better word, and a hyperthreading core or an SMT core is like a child or a sibling core, which is not quite as fast as the parent. But when we add those full cores and hyperthreaded cores or SMT cores together, we end up with total execution threads. These are the number of CPUs, or in a hypervisor the number of virtual CPUs we have to play with. The next thing then is RAM, or random access memory. Called random access memory because previous versions of memory worked in a linear fashion and you had to rewind or fast forward through the memory or through the tape, a little bit like you have with a cassette tape and a CD. RAM is random access, like a CD, you can jump from one place to another, whereas with a cassette tape or linear RAM you had to rewind or fast forward to get to the right place. So that's the historic name for why it's actually called RAM. And this is the working area or space that the operating system and other applications run in. The more RAM you have, the more applications and services you can run at the same time. A good way to think of this is like having desk space. The bigger the desk you have, the more things you can have out at once, and when you run out of space you have to put things away before you can get new things out. So it's like the working area for the computer to do its job or to do its work. And again, common names you'll see associated with things like RAM or Corsair, Kingston, Hynix, Samsung amongst others. So one of the key things about RAM is that it has memory loss. The contents of RAM are lost every time the computer is powered off or restarted. So in computer terms, that's non-persistent or volatile. So when we say RAM is non-persistent or volatile, we mean it loses the things stored in it when the computer is powered off or turned off or crashes. The advantages of RAM are that compared to many other parts of the computer, RAM is extremely fast. So applications and services are loaded from a disk into RAM to allow the CPU to work with them. So this is the fastest storage mechanism we have on the computer, but the problems are it's not persistent. So we have to store the information somewhere else. We'll commonly use a hard drive or solid state drive to do that, but RAM is where the work is done, and drives are where the information is generally stored. The number of RAM slots you can install in a computer depends on the motherboard, but sometimes you'll find that the RAM slots are associated with the CPU. So if you have a motherboard that expects 2 CPUs and you only fit 1 CPU, you might find that only half of the slots are available because the slots rely on the CPU to work. So in this picture you can see here, you can see there are 2 motherboard sockets but only 1 processor fitted, the blue processor with 4 cores, which means that only the RAM slots to the right hand side in blue are the ones that you can put memory into and it work properly, because the other sets of RAM slots, the yellow ones, won't work until you put the CPU in the corresponding socket next to it on the left. And again, just an explanation of why we get the name. RAM chips are often called DIMMs, and that comes from the package or the type of memory that we use. So the format of the memory stick is something known as a dual inline memory module, which is where we get the name DIMMs from. If we now move on to disks or storage devices. Disks are where the operating system, applications and application data is stored. And the important thing about disks is that they need to retain information even when the computer is powered off or restarted. And for that reason, disks are known as persistent or non-volatile devices, which just means that they keep your information safe even after the computer's been powered off. Names that you'll see associated with various types of disks and drives are Western Digital, Seagate, Hynix, Samsung. And that's because there's 2 different types of disk. There's a hard disk drive or a HDD. This is a mechanical device that uses a spinning disk or head that moves across the disk a little bit like a record player. Things to know about hard disk drives or HDDs are they are slow when compared to an SSD or a solid state drive, but they're low cost and they're high capacity. On the flip side of that, a solid state drive is very fast when compared to a hard disk drive, but it's got a high cost and a low capacity. And these work by storing information on memory chips that don't lose information when the device is powered off or restarted. So hard disk drives and solid state drives do the same job, but hard disk drives tend to be low cost and high capacity. Solid state disk drives tend to be high cost and low capacity. And in some systems you'll see a mixture of both types of drive, something we will call a hybrid system. Next on the list is a network card, or a NIC, a network interface card. This is the device that connects the computer to the network by a cable made of copper wire or fiber optic strands. And most computers connect to other computers in the same building or over the internet using something called TCP/IP, which we'll talk about next. Common names you'll see associated with network cards are Intel and Broadcom. And the important thing to know about these is that all modern networking systems use something called the OSI model, or the Open Systems Interconnection model, and it's just a standard for describing how every part of a network needs to communicate with every other part of the network. And the OSI model breaks this down into 7 distinct layers, we're only going to talk about a few of them, and that's just because you'll hear these terms used in networking circles without very much explanation of what they do. It's just expected that you hear the term, you would know what it means. So the first thing we're going to talk about is network cables. You'll often hear network cables referred to as Cat5 cables, even though modern ones are Cat6 or Cat7. It comes from the original term, which meant a cable that meets the Category 5 specification. But you'll often hear network cables that are either Category 5, Category 6 or 7, still referred to as just a Cat5 cable. And a Cat5 cable is a cable that transmits data between network devices, and we say that a network cable operates at layer 1. We will talk about this a little bit more, but just to say that layer 1 is about the cable that connects the network, whether that be made of copper or fiber optic or any other type of cable. The thing that we plug the cables into is usually a computer at one end and a switch at the other. And switches are devices that are used to connect devices together on the same network. So if you had 10 computers in the same room, you'd probably have 10 cables plugged into one switch, because that's the device that connects all the cables into the same room. If you wanted to connect to another 10 computers in another town or city or building, the chances are that the switch would then be plugged into a router. And a router is a device that connects multiple networks or switches together so that you can route information between them. So what we have here is cables, which are layer 1, switches, which are layer 2, and routers, which are layer 3. And these terms will become important when we talk about network and security later on in the series. When we try to do layer 2 over layer 3, it's just important that we understand what that layer 2 and layer 3 actually means, otherwise it's just a term or an acronym that makes no sense. So that's network cards. The next thing we have is graphics cards, or graphic processing units, or GPUs. And a GPU is a little bit like a CPU, but this time it's got thousands of cores specifically designed for graphics and mathematical processing. But although it's got more cores, these cores are much simpler than CPU cores and are used to create computer graphics through something known as shading. And depending on the make and model of the graphics card, a shader goes by different names. AMD calls them stream processors and Nvidia calls them CUDA cores. But essentially it's a large amount of very small processors on a board designed to do lots of things at the same time. Names you'll commonly see are ATI and Nvidia. And you quite often see these graphics cards put in servers because we can use them for end-user computing solutions, EUC, or things like VDI, Virtual Desktop Infrastructure. So you'll see things like VMware Horizon View using expensive graphics cards in a server to provide tens or sometimes even hundreds of desktops in a single device, and it improves the graphic performance of virtual machines that might be used by tens or hundreds of users on a network. So that's the traditional use you'll find for a graphics card in a server. But other things we can do with them are things like artificial intelligence. As I said, the large number of mathematical processing cores that we have in a GPU and the parallel nature of how it works means that GPUs are a fantastic way of improving performance of things like AI or artificial intelligence. These graphics cards and processing cores can also be used for something called machine learning. So again, these thousands of cores that can perform lots of mathematical calculations in parallel mean that they're great for machine learning. So although traditionally we put graphics cards in servers for end user computing and VDI, the uses for them going forward will most likely be more around artificial intelligence and machine learning. So next on to power and cooling and power supply units, or PSUs. So a PSU is used to provide all the power required to run a computer. You quite often see these with several fans that blow all the hot air out of the back of the computer while sucking cold in at the front, or sometimes sucking it in from the bottom and blowing it out of the top. An important thing here to remember is that for every 3 watts of power a computer uses for running its applications and services, we're going to need at least another 1 watt of power to remove the heat generated from it with an air conditioning unit. So not only is the amount of power that a computer or a server use important, we've also got to take into account the extra wattage we're going to need to cool it down as well. So when we talk about power and cooling in server rooms, we tend to have something called a UPS, or an uninterruptible power supply. And this is a way of keeping servers running during a temporary power outage, or during something we would call a brownout, where the power disappears for a period of time. And essentially a UPS is a large industrial battery, or a set of large industrial batteries in between the power supply, the electrical power supply, and the server, and their job is to keep the computer running for long enough that all the applications and services can be shut down cleanly. It's common for UPSs to only last for maybe 15 minutes to 30 minutes. It's not expected to keep the whole computer environment running indefinitely. It's just long enough to shut things down cleanly so we don't lose any information. So the other thing here is power. As processing power increases, it's getting harder and harder to run modern processors, and energy efficient processors are now starting to become more expensive than fast processors, even though they're obviously slower than the other processors. But the energy efficiency part has now become more important than the speed part, because most people can afford an expensive processor to put in a server, but they don't have the means to cool it down, or they're running out of capacity with air conditioning in a server room. So cooling has now become one of the largest problems faced by IT managers, and it's not uncommon to see an IT manager trade performance for efficiency, because unless they trade performance for efficiency, they can't put any more computers or servers in the server room. And speaking of servers and server rooms, we tend to group multiple servers together in what we call a rack. And to do that we use rack mount units, or for simplicity just U's. So a modern server is rack mountable, and it slides in and out of a rack, something that looks pretty much like a baker's rack that goes in an oven. They're commonly used in data centers to house several servers in a small amount of floor space. So it wouldn't be uncommon to see a rack that's no more than a couple of feet wide by a couple of feet deep, hosting maybe 42 servers at once in a very small amount of footprint in the data center. A 1U rack mount server occupies a single U in a rack, and a 2U server, it makes sense, would occupy 2 U's worth of space in a server rack, and a U is 4.5 millimeters or 1.7 inches high, and a full rack is normally 42 U's high. And what this means is that data centers can all be built to the same specification, and you can be reasonably confident that whoever you buy your server equipment from, it will fit in the rack in a standard way, and you know just how many devices you can get in every rack because they're all measured in these U's. So the most common type of server that I see in my day-to-day work is a 1U server that most people call a pizza box, because of the similar shape and size to a pizza box when you pull it out of the rack on rails to slide out to either install it or service it or remove it. You can also see bigger 2U, 3U and 4U servers for larger systems, things like ERP, Enterprise Resource Planning, CRM, which is Customer Relationship Management, and other applications that require large amount of CPU and RAM. But the trend now is to move to a different model, which is called hyper-converged infrastructure. This is where the server, the network and the storage are all self-contained in a single unit, and this makes it more efficient because everything's in the same place or the same box, without some of the connecting networks or connecting fabric that in the past has made this a little bit slower, because the speed of the server is limited by the speed of the fabric between the devices. So put simply, if you put everything in the same box, it runs faster than if you put it in different boxes and join it together with slow networks or slow connections. So HCI, or hyper-converged infrastructure, is rapidly becoming the most cost-effective and highest performance method of connecting commodity devices together, storage devices and server devices, into what we would call a virtual SAN, or vSAN. The next thing we need, once we've got the server hardware together, is an operating system, and this is the environment that applications run on. So an operating system sits between the applications and the hardware and does a lot of the translation so that a programmer doesn't need to understand everything about the hardware underneath. He or she would just ask the operating system to do something, and the operating system takes care of the interaction between the applications and the hardware underneath. And the one that most people are familiar with is Microsoft Windows, but others are available. And as I said, the operating system sits between the underlying hardware and the applications and services that run on top of it. And this means that an operating system and services can be written by programmers without the programmer having to understand all the specifics of the hardware in great detail. So the programmer can just ask the operating system to open a file, save a file, print something, and the operating system will do it for the programmer without the programmer having to write that piece of code or that piece of software to do it. So the programmer writes the application for a particular OS or operating system, and the operating system takes care of managing all the underlying hardware for them. Other types of operating system are Apple iOS and OS X. So iOS is used on Apple tablets and phones, and Apple OS X is used on Apple MacBooks, MacBook Pros, and Apple workstations and iMacs. We also have Linux or Linux, and Linux is used on millions, if not billions, of devices, ranging from the smallest devices, the IoT devices or Internet of Things, right up to the world's largest and most powerful supercomputers. There's another variant of Linux called Android and Chrome OS. So although it is technically based on Linux, it's so popular and so widespread that we're giving it its own little section. So Android and Chrome OS is an operating system produced by Google, and it's used on a large number of tablets, phones, things like the Samsung Galaxy range of devices, and things like Chrome OS are used on things like Google Chromebooks. So that was an overview of the hardware used in a data center, and the next section will be the evolution of the data center all the way from the 1940s to the 1990s.